Welcome to Chapter 2, The Language and Logic of Geometry, and our first lesson, 2.1, The Need for Definitions. So the main idea of this lesson is that the purpose of definitions in mathematics, and as you've noticed, geometry is heavy in definitions, but the purpose of mathematical definitions is kind of twofold. It is first to provide clarity, and second, to help to communicate ideas of mathematics. So, example of that would be, if we look at this question, what rectangles appear to be, and a key phrasing here is appear to be, which we'll explore in a little bit. So which rectangles appear to be in the figure at the right? Name them. And remember, we name any polygon by its vertices or corners, and you just have to name them in order of the 4 points. So we name them using the 4 points in any order going around the figure, this case rectangles. So we would have 6 of them: RELU, ULSM, ETNS, RESM, RTNM, LGAC. So we would have 6 different rectangles looking at this figure, or what appear to be rectangles. Then we move into this main idea, exploring that phrasing of appears to be. So in mathematics, it is not possible to decide which figures in example 1 here are rectangles without a careful definition of a rectangle. So remember, these definitions provide clarity and help us communicate. So if we look at any of these, they don't give us any symbols, any measurements, any labels. All they gave us were the labels on the vertices, nothing else. So if we further explore that, here we have a rectangle ABDC, or ACDB, however we want to name it, going around the vertices. We would say that this figure, this polygon, appears to be a rectangle, but without any measurements, labels, or symbols, we cannot say for sure, because the definition of a rectangle tells us that all the sides meet at 90-degree or right angles, and that the opposite sides are congruent. So we would have to know that AB was congruent to CD, and that BD was congruent to AC, and that all 4 corners were 90 degrees for us to say for sure this figure is a rectangle. So our example down here, we can say for sure is a rectangle, because if we know that this figure EFHG has 90-degree angles, given here with our symbols in the corner, we have 4 90-degree angles, and we have 2 pairs of congruent sides, which are opposite each other. GH is congruent to EF, because they both have the double hash mark. And then we know FH and EG are congruent with the single hash mark to each other. So the idea of a definition, if it is in a visual form, which we get quite often in geometry, in order to say something is definitely something else, we need to make sure that it qualifies for all parts of the definition. So further exploring this idea of good definitions and the need for definitions in geometry, we have 6 figures shown below. They all have characteristics in common. So definitions are made up of characteristics. They all have straight sides and are what we would call enclosed regions. And by enclosed regions, that means that all the sides meet at their vertices and they intersect two other sides. So these are the characteristics of polygons. Polygons are not limited to 3 or 4 sides. The two figures at the right are heptagons, or 7-sided polygons, which we'll explore later in this definition, or later in this chapter. But when we are classifying our polygons, we classify them based on their number of sides. So all these figures here, these 6 figures, are all polygons. Polygons have sides that are made of line segments, so we know that they are straight, they are not curved. And those sides intersect exactly two other sides at their endpoints. So that would be our simple definition of a polygon. And then they create what we could also call enclosed regions, the interiors of these polygons. So example 2 says, which of these figures do you think appear to be polygons and why? So when we name that, we would say only C and E are polygons, because the other part, which I forgot to put in our simple definition here, is polygons are all two-dimensional. So they're all on a single plane. They don't have multiple planes. So that means D would be out. So C and E are only two polygons. They are enclosed regions made up of segments that intersect each other at exactly 2 points, or at their end points. B could not be because it has a curved side. A is all made up of segments, but these segments do not intersect at their endpoints. And like I said before, D is 3-dimensional. Polygons are only 2-dimensional. So then we get into these definitions of convex and non-convex. Non-convex sometimes is referred to as concave. They're interchangeable in geometry. So a convex set has a little bit of a complex definition. It's the set of all points in which every segment that connects points of the set lies entirely in the set. So figure 1 at the right over here is kind of an example of this definition. Or not really kind of, it is an example of this definition. So figure 1 is what we would call a convex set, because the set itself of all the points, so all the points in which every segment connects points of the set, lies entirely in the set. So in other words, I like to explain it using the definition of a convex polygon. Convex polygon is a polygon in which no side of the polygon, which we know is contained in a line, so no side of the polygon has a point on the interior of the polygon when it's extended into a line. So if I would extend all these segments into lines, so every segment along the exterior of this figure is extended into a line. When that happens, all the points are inside the set. Not a single point on these sides would end up outside of the set. Everything's contained on the interior. Or if we look at the idea of a convex polygon, because this figure is a polygon, if we extend all the sides and not a single side cuts through what we would call the interior of the polygon, then it is convex. So the easiest way to think of convex is if we extend all the sides into lines, do any of them go through the interior? If the answer is no, then it is a convex set or a convex figure. If we look at figure 2, when we extend the sides, some of them, when extended, would not go through the interior, but others pass through the interior. So if sides pass through the interior, then that set is not convex, or what we would call a concave set or concave figure, or if it's a polygon, a concave polygon. So non-convex and concave mean the same thing. So that convex set definition is a bit more hard to understand, but if we think of it based on a convex polygon, it's a little easier to understand. But our geometric definition, a convex set is the set of all the points in which every segment that connects points of the set lies entirely in the set. So in example 3, we're determining whether each figure is non-convex or convex. So what I do with all of them is you can just imagine each side of the figure extended into lines going on forever. None of those lines pass through the interior, so it's convex. In figure 2, these lines, when extended, would pass through the interior, so that would be a non-convex or concave set. And then in figure 3, first what we need to realize is figure 3 is not a single polygon or a singular polygon, but rather two individual polygons, a triangle on a triangle. So this point of intersection, well, points technically don't have any space. So this point would not necessarily be on the interior because these two individual polygons simply meet at that point. So each one of these individual polygons, when these sides are all extended, would be considered convex. So each one of these in this figure 3 are convex polygons. So when we're looking, though, at the idea of definitions in mathematics, the idea of definitions, as you'll explore in these practice problems, are to help to provide clarity when exploring different things, such as figures, and for helping us communicate about different mathematics.